Hello, this is Dr. J back with another episode of my Commander X16 game development devlog. We've added a lot of functionality to our library now. We've defined a metadata format for our graphics, added functions for loading them and moving them around in memory, then we added structs and functions for handling animated sprites. And after that, we pulled in a custom font set and added some text drawing routines. Next up is handling user input. The Commander X16 makes retrieving the state of various input peripherals pretty easy, with just a couple of calls to the kernel, but there are still some things we can do to simplify working with user input. Since my focus is on making retro-style games like those found on old game consoles, my main focus is going to be handling joypad input, specifically the SNES controller that the X16 is designed to support. I'll also add the same kind of convenience functions for handling the mouse, but for the time being I'm going to put off convenience functions for keyboard input and leave that for another day. One issue is that the Commander X16 returns the state of the joypad in 2 separate bytes. It's not that big a deal, but personally I would rather just check a single variable to get different button states. So I've defined a function that pulls the X16 for joypad state, then combines the bytes into a single short and returns it. Also, the X16 defines 1 as meaning a button is not pressed and 0 as meaning it is, which to me feels kind of backwards, and I find it more convenient to work with when it's the other way around, so I also invert the bits in the short before I return it. Then I define some macros so I can easily compare the returned short with the bit masks corresponding to each button. Just use the bitwise AND operator with the short and you can tell which buttons are pressed. There's another bigger issue we'll want to address, and that is, a lot of the time, you don't just care whether a button is currently being pressed right now. You care about whether the button was being pressed and has just now been released, a state which is called a falling edge. For example, imagine a situation where the player is navigating a menu. You don't want to count it as a menu confirmation just because the A button is currently pressed. Otherwise, unless the player is so fast they can keep the button pressed for just 1/60th of a second, it will count as a whole bunch of confirmations every time they press the button, which could lead to a lot of unintended consequences. And there are plenty of other situations where we want to respond to a button that has just been released. So I've defined another function for exactly that purpose. Just make sure to keep track of the state of the buttons during the previous iteration of the game loop to compare to their current state, and you can call this function to determine which buttons have just been released this frame. I've also created the same functionality for the left and right mouse buttons, as well as a function to save the current mouse position, which is saved into 2 pointers, exist mouse X and exist mouse Y. I've put together another program to demonstrate input handling, but actually I've done a lot more with this one. I've applied some improvements and optimizations to some of the functions we've talked about in previous videos. So let's cover those before we show the demo. First, I've added a parameter to the prepare sprite function, a boolean which, if set to false, will skip the step of copying the graphics from high RAM to VRAM. This is useful if you have a large number of sprites that share a common graphic, as is the case in the demo I'm about to show. It will save a lot of unnecessary data copying. Next, I added a posX and posY field to the sprite struct. This technically isn't necessary because you can get the sprite position out of the sprite metadata in VRAM, but accessing it here should be both more convenient and more performant because getting it out of VRAM involves querying it through the Vera and pulling it into a local variable, which if we want to be convenient about doing that, we have to put it into a function. It does have the downside of adding 4 bytes to the size of our sprite structs, but this can be counteracted by reducing the size of the sprite bank. Most games probably won't have 128 active sprites at the same time. So for this demo, I've reduced the size of the sprite bank to 64 sprites, so now it's actually using less memory, even though each struct is bigger. On a similar note, I've also added a convenience function, update sprite position, which updates the position of the sprite in VRAM. Remember that even though we added an XPOS and YPOS parameter to our own sprite struct, that's just for our own convenience, and as far as the Commander X16 is concerned, those values don't mean anything. They only become meaningful when we copy those values to the right addresses in VRAM, and this function takes care of updating values for us. Next is the process sprite function, where I've applied a simple performance optimization. Previously, this function accepted just a single sprite index for processing. But the downside of that is, it means you have to do a function call for every sprite you want to process. Function calls are relatively expensive operations even on modern CPUs, but I believe, and take this with a bit of a grain of salt, because I still have yet to study the 6502 architecture in detail, so my confidence interval here isn't quite 100%. But I believe the 6502 doesn't have hardware support for a call stack, which means the CC65 compiler has to emulate a call stack to manage function calls and parameter passing using zero page and stack memory, which comes with more overhead than normal. That means function calls for us are more expensive than normal, and we want to minimize them. So I updated the process sprite function to take a range of sprite indices to process, so you can update a whole bunch of them with a single function call using iteration, which will be faster, maybe significantly faster. I haven't verified just how much of a performance improvement this gives us, but I'm willing to bet it's probably non-trivial. Finally, I added a very important utility function which will be needed by the majority of games. As far as I'm aware, the Commander X16 doesn't have any built-in capability for generating random numbers. So I added a very simple random number generation function employing a linear congruential generator, which sounds much fancier than it actually is. The function accepts an inclusive range of numbers and returns a pseudo-random integer within that range. It does need to be initialized with a random seed to generate a different sequence of numbers on every program run, which creates a bit of a chicken and egg problem. The best method I can come up with to seed the random generator with a somewhat random seed, which is a tried and true old school method for seeding an RNG, is to get the frame counter the first time the user presses a button, and use that as the seed. That said, my demonstration program takes a cop-out approach and just uses a fixed seed so it will generate the same sequence of numbers every time. But a real program should theoretically be able to use this function to generate pseudo-random numbers. Okay, that was a lot of explanation. Let's start taking a look at this demo. Well, I guess there's still a bit of explanation left to go because this demo is doing a bit more than the previous ones. I've pulled in my ship sprite from a couple videos ago, but this time we have the ability to move it around the screen. Now ordinarily, when moving a ship, you would just want it to move every frame as long as the corresponding button is pressed. But just for the purposes of demonstrating our input checking, here we're only going to move the ship when the button is pressed and then released, which is to say on a falling edge. To demonstrate the same functionality for the mouse, we'll also jump the ship forward if the left mouse button is pressed and released, and jump it back for the right mouse button. None of this makes sense from a gameplay perspective, but it's just to test our input reading functions. The other thing I'm doing with this demo is stress testing the X16 library a bit. I made a simple animated star sprite and I'm initializing it with 32 of them, randomizing their positions, and then scrolling them down the screen so it looks like we're flying through a star field. Granted, this isn't quite going whole hog by flooding the screen with the maximum of 128 sprites, but honestly, considering the performance hit we're taking by using C instead of handcrafted assembly, if I can even display 32 simultaneous animated sprites on screen with no hint of slowdown, I'll feel like the library is doing a pretty good job. The last thing I'm doing is grabbing the mouse X and Y positions and using our text drawing functions to display those on screen, just to show that getting the mouse position is working correctly. Okay, now the explanations are done for real. Let's give this thing a try. Alright, so let's take a look at our main function. It's a little bit more substantial than the past examples we've looked at. So I go ahead and define some variables that we're going to need. The ship X and Y position, a clear counter for blanking out strings. Total number of stars is going to be 32, and then I'm going to keep track of the starting positions of the stars, because the way that I'm implementing them scrolling past the screen is I randomize their positions above the top of the screen to start with, scroll them down until they go off the bottom of the screen, and then reset them back to where they started. So that's why I have to keep track of their starting positions. We have a process input function. And just in case it's not clear, these are not actual functions in the X16 library. All of this is just for the demo. So we have a process input function. So when one of the D-pad directions on the joypad has been pressed and then released, which is to say it has a falling edge, we update the ship's position accordingly. As I mentioned, this isn't how you would implement it in a real space shoot 'em up kind of game. This is just to prove that the falling edge checking works correctly, because that's the marginally more complicated thing to do. And then if the left or right mouse button is clicked, we jump the ship forward or backward by 15 pixels. And then we call our new function to update the sprite position based on our updates to the ship X and Y values. And then we have a function for moving the stars from the top to the bottom of the screen. All right, and then we do some initialization. We initialize some local variables that we're going to need, turn on 320 by 240 mode, enable the mouse. Now here's an interesting side note. I originally thought maybe I could just generate a random seed from whatever the mouse position is at the program launch, because that should be relatively random. But I discovered, and I haven't figured out why yet, that if I call my update mouse position function this early in the program run, it actually crashes the emulator. Strange. Like I said, I haven't figured out why that happens yet. But at that point, I decided, all right, I'm just going to do a cop-out. I'm just going to initialize my random number generator with a fixed value for the purposes of this demonstration, just to keep things simple. So then we call some exist initialization functions, initialize the tiles, the text, load in our sprite metadata, enable sprites. Then we load and prepare the ship sprite with our load and prepare sprite functions. Then we initialize the stars and randomize their Y positions. So we load the little star animation into HiRAM, loop through each of our stars, randomize its Y position using our random number generator. We just spread them across the screen from left to right widthwise in a uniform manner. Then we call prepare sprite to copy from HiRAM to VRAM. And for the very first star, we do have to copy the graphics from HiRAM into VRAM, so we set that to true. But at that point, since they all use the same graphic, it's now loaded into VRAM, so we don't need to do that again. So after we do it for the first star, we set that to false, and prepare sprite sets up everything else that's necessary, but doesn't do the graphical data copy. So that just saves us a lot of unnecessary data copying. Nice little optimization there. And then, so that they aren't all on the exact same frame of animation to start, because that would look kind of boring, we vary which frame of animation each one starts on, whether it's the first or second, because it's only a little 2-frame animation. Then we enter our main game loop. So we get the current state of the joypad, and at the end of our main game loop, we set what the previous state of the joypad and button were, so that we can keep track of that to figure out which edges are the falling edges. And we'll pass that as information into the get falling edges function, and that's how you set that up. So it's not especially difficult. You just need 2 variables, one for the current state of the button presses and another for the previous state of the button presses that you feed into the get falling edges function. And we do the same thing for the mouse, and we also update the mouse position, which interestingly does not crash the emulator when called here. Then we call the process input function that we defined up above for moving the ship around, because now we have the information that we need to do that. Then we call the move stars function to scroll the stars to the bottom of the screen, and then put them back off the top once they scroll off the bottom. And then we do some text printing. We convert the X and Y positions of the mouse into strings, and then draw those strings in the lower left and lower right corners of the screen. Then we call process sprites, and since we optimize it to accept a range, we only have to call it once, and we pass in the range that encompasses our ship and then our 32 star sprites. And I am not doing this immediately, so I can actually comment this out. But one thing that I did do was have a game counter going so that I could get a good gauge of whether the emulator was running at full speed or not. And we'll check that out in a moment, but for the time being, I'm just going to comment that out. Okay, so that pretty much summarizes all of the functionality of this demo. That warning is not a warning that comes from the library. That warning is just because I've done a couple different things with this demo and commented out some code. And so I'm not using all of the variables that I have defined each time I compile it. But the library itself is warning free. One quick note is obtaining the mouse position is not going to work perfectly immediately, and the mouse cursor might not show up immediately because it seems to take a moment for the emulator to get a handle on the mouse. Maybe that has something to do with why this crashes if called so early in the program run. And I also am going to have to remember to hit Control-M so that the emulator captures my mouse cursor. Otherwise, the position of the mouse in reality is not going to perfectly match the position of the mouse that the emulator thinks it's at. All right, so let's finally see this thing in action. We've sure been talking about it a lot. All right, and then I hit Control-M to capture the mouse. There we go, and there's our mouse cursor. And you can see in the lower left and lower right corner are the X and Y position of the mouse respectively, and that they definitely seem completely accurate. And we can move our ship around by hitting the D-pad buttons. I'm actually using my keyboard. If you don't have a SNES plugged in, then certain buttons on the SNES controller are mapped to keys on the keyboard. So you don't actually need the SNES controller in order to use the joypad input. So you can see that all that is working, and if I click the mouse button, it jumps us backward and forward more quickly. So we can see that that's working as well. All right, so that's pretty cool. And I hit Control-M so that it's no longer capturing the mouse, and I can move it outside the emulator again. And now, in order to do some proper stress testing, I went ahead and added another counter here for counting the number of seconds that have passed, at least according to the program, because it should be running at 60 hertz. So every time the game counter is divisible by 60, we should be able to increment the second counter. And then down here in the main game loop, I have commented out the parts where we were displaying the positions of the mouse cursor. And now we're going to increment the game counter. Every 60 frames, we're going to increment the second counter. And then we're going to display the frame counter and the second counter in the lower right corner of the screen. I'm going to run this in two different ways. I'm going to run it as is with everything executing, and I'm also going to run it with the process sprites and the move stars and the processing input all commented out so that it's doing as little as possible. I'm going to capture how it performs under both conditions, and then I'm going to put the two runs right next to each other so we can see if their performance is equivalent and if they both seem to be running at full speed. So that would clearly be a no. The version where we're running everything seems to be running about half the speed as the version where we commented most of this stuff out. And I went ahead and did another test where the only thing I commented out was process sprites, and I left everything else in. And I got that same slow result. So process sprites is definitely the bottleneck here, and it's causing us to run at about 30 frames per second instead of 60. So we're going to have to find some ways to optimize this thing in order to squeeze some acceptable performance out of the little engine we've built here. Okay, so I found a link that I had saved to this GitHub repository with advanced optimizations for CC65. And a lot of these are pretty much what I was expecting. Scroll down a bit here. All right, so... All right, well, the first one I didn't know about. It gives additional compiler optimizations beyond just the capital O. So it's got OSIR, which enables optimization of code, inlines known functions, and enables use of the registry keyword, and then CL or static locals, which makes static local variables instead of putting them on the stack. So I went ahead and I'll update my make file with these additional compiler optimizations. Smallest possible unsigned data types I was pretty much already doing. I've been pretty meticulous about always using the smallest data type I possibly can for a given variable. So that one, I can already put a check mark by it. This one did not surprise me at all. So what I was saying about how the 6502 doesn't have a proper call stack at all, and the CC65 compiler has to do software emulation to make its own stack. This page confirms that, and it makes it sound like it's even worse than I realized, that it's just really slow. And I had thought that maybe eliminating function parameters and changing them to global variables would be a solution, and this page is confirming that. So that's definitely useful to know. And although it will make code less readable, it is a relatively easy optimization to apply. This one's interesting. Replace array of structs with a struct of arrays. So instead of having a struct with all these types in it, and then an array that contains those structs, which is a very natural, common thing to do in C programs, and as you've seen, that's what I've been doing. Apparently, this doesn't work especially well with the 6502, as a side effect of it being an 8-bit processor and needing 16 bits to address available memory and so on. So what it suggests as an optimization is to move the arrays inside the struct, not have a struct of arrays, and then instead of having your references to the struct be like struct name, or rather struct array, index into the struct array, and then the struct field, what you do is you have the struct, the field, and then the array index into that field, because now it's that field that is the array. So that's an interesting one. And that's another really easy optimization to apply. And in my opinion, it doesn't even really reduce the readability of the code. I mean, this versus this, one is just as easy to read as the other. So that's nice. I wasn't using enums anyway, so number 6 doesn't apply. Number 7 is place commonly used variables on 0 page. I think I'll skip that one unless it turns out that other optimizations aren't helping. Getting rid of parameter passing. Then replacing calculation switches, discrete access by using lookup tables, and so on. There's quite a lot here. But I think I'm going to start with basically just 5 and above. I'm going to apply all these optimizations, at least all the ones that I haven't already been applying, and see what kind of speed up we get just from doing these. Maybe it'll be significant. Let's hope so. All right, I had to take a little break to do some other things, but then I went ahead and applied the optimizations, or some of the optimizations suggested by that GitHub repo. So here in the exist sprite struct, as you can see, as the repo suggested, it is no longer an array of structs, but a struct of arrays. And yeah, like I thought, I mean, it's very easy to make this adjustment. The code hardly even looks any different, so it doesn't really hurt code readability. And then the other major optimization that I've applied is I have removed the parameters from the exist process sprites function call, because we know that's the bottleneck, and moved the parameters into global variables. So the start index and the end index are now defined as globals. This does have a little bit of an impact on code readability because calling the function is a little bit less convenient now. It's not a huge deal. You can see the call to it here. It's just that now you have to assign the parameter values to the global variables first, and then call the function. instead of just assigning the parameters, directly into the function call as arguments. So it does impact code readability a little bit, but it's not too bad. It's not a super ugly optimization or anything. And the other function besides process sprites that I can imagine getting called very frequently is the text drawing functions. So I went ahead and applied the same optimization to those. Took the parameters out, as you can see, moved them into globals, which are now exist text, and then the X and Y coordinates for where to draw the text. I went ahead and kept the typewriter text and the regular text coordinates separate so that you can be doing both at the same time. And I didn't need to do anything with the typewriter text string or array of strings because that was already a global. So that optimization had kind of already been done. And you can see that's definitely a little less convenient now. We have to assign the string that we want to print out and then assign the coordinates and then do the function call. A little less readable, but again, not that big a deal. As low-level optimizations go, this is not hideous stuff. It's not turning our code into an unreadable mess. The real question, though, is, did it do anything? Is our game actually going to run faster now? I guess just one more thing that I'll mention before we run another test to see the results. I didn't apply these optimizations to everything. As you can see, there's still a fair number of function calls where I'm just passing the parameters in as normal arguments. And the reason is because not every one of these functions is a performance bottleneck. And you don't want to necessarily optimize everything in sight, uglying up your code left and right, if you're not really going to get any kind of major performance benefit out of it. So I'm just targeting what are going to be the bottlenecks. Process sprites is definitely going to be a huge bottleneck, and text drawing probably will too. So those are the two I targeted. Those are the ones where we stand to gain some real performance by applying some optimization. The rest of them don't really matter as much because they're not going to get called as often. They're not going to be part of our core game loop and thus need to be super tight. All right, so let's go ahead and watch this in action again. I'm going to go ahead and put it up next to the original run where I disabled everything so it wasn't doing anything, so it was running at maximum speed. And I'm also going to put up the slow run that we saw earlier, and we're going to see how the new one compares to those two. All right, fingers crossed. Let's hope all these optimizations have paid off. Nice. It actually worked. Just with a couple of simple optimizations, taking out the function arguments and making them globals, and using a struct of arrays instead of an array of structs has enormously boosted our performance, and now our game is running at full speed even while animating all 33 of the sprites in this example. I am really excited that fixing the performance problems was that easy. And that just goes to show how important it is to know a little bit, just a little bit, about the architecture of the CPU you're targeting when you're doing this kind of really old school development. Just knowing a little bit and making some tweaks to your code can make such an enormous difference. But I'm really excited. When I saw how bad the performance was at first, my heart sank a little bit, and I was worried that getting the performance up to scratch was going to be a real pain and take me a long time. But it didn't. It was actually pretty quick and easy, and that is a relief. And now knowing that the core parts of the library that really matter are adequately performant, we can move on to the next part of our library, which is almost done. It is almost ready for its initial release at this point. We just need to apply a little bit of stuff for using the tiles, not just for text, but for arguably their primary intended purpose, which is rendering terrain and maps and background graphics. And we're not going to be immediately implementing everything that I would necessarily like to have for that. We're just going to go with the bare essentials that we need to get up and running. And I'm going to get into the details of that and the reasoning for it in the next video. And taking care of the tiles and any other miscellaneous cleanup things next is probably going to be the last development video on the library, the Exist16 library for now. And then I'll be able to get to the really fun part, which is kind of the whole reason I've been putting this library together, aside from hoping that it's useful and convenient for the wider Commander X16 community. But for my own personal selfish purposes, I finally get to start on the really fun part after we wrap up the Exist16 library, which is using it to start making some actual games. But let's not get ahead of ourselves. There's still a little bit left to do. So hopefully I'll see you for that in the next video for some more retro game development goodness.